So the response to my last video, Planck's constant and the nature of light, was actually quite interesting. I expected a more negative response because what I'm saying is quite controversial. But in reality, the response was actually pretty good. Many people were getting what I was saying. I think this is the very first time that I actually broke through. I've been trying to explain this to people for years and years and years, and I always get a negative response. And so this is the first time that I feel like I'm getting through to people. So I want to take this a little bit further today and talk about these two equations that you see on the left here. These two equations are used to convert from the frequency domain to the wavelength domain and back again. So I'm going to show you how modified unit analysis deals with these expressions. Okay, so lambda is wavelength equals the speed of light divided by frequency. So if you have a frequency of light and you want to convert it to wavelength, you use this expression. So in modified unit analysis, okay, the units of lambda are meters per cycle. Okay, and you can see that on the right because the units for the speed of light are meters per second, and the units for frequency are delta per second. But because this is in the denominator, you write seconds per delta. Okay, and the seconds cancel and you get meters per delta. So in modified unit analysis, the units for wavelength are meters per cycle. Okay, this equation converts from the domain of frequency to the domain of wavelength. But there's a deeper meaning. And I'm gonna start from scratch here. I'm gonna write it up. Okay, so I'm gonna write this again. Wavelength is equal to the speed of light divided by the frequency. Now in modified unit analysis, the units of wavelength are meters per cycle. Okay, so you can see this on the right where the units of the speed of light are meters per second, and the unit of frequency is cycles per second, but because this is in the denominator, you reverse it. So the units, so I write seconds per cycle. The seconds cancel and you get meters per cycle. So the units of wavelength are, in modified unit analysis, are meters per cycle. In modified unit analysis, I added the domain of oscillation to the other domains of space, time, and mass, which we'll talk about later. Okay, I add a domain called oscillation, and the unit of oscillation is cycle. So this is basically the only difference between modified unit analysis and standard unit analysis, but it leads to a different interpretation of light, and this is what I'm trying to get at. So this equation right here, okay, converts from the frequency domain to the wavelength domain. But it does something else. It is a conversion from the frequency domain to the wavelength domain. That's totally true. But it's also a conversion from the domain of per second, which frequency per second, to the domain of per cycle. Okay, this is a transformation from the domain of per second to the domain of per cycle. Okay, so now I'm going to write the equation that I've been focusing on. E equals HF. And there's a little t in there that got set to 1. Okay, so in modified unit analysis, there's a little time parameter in there, and this is where the extra unit of s belongs. Okay, so this equation is, because there's a frequency term, this is written in the domain of per second. Per second. So this equation can be nothing other than the energy of a 1 second time interval. Okay, 1 second is an arbitrary time interval invented by man, humans, okay, because we have, this is the cycle of man, okay, this is our heartbeat. This is man's cycle. Man, and there's a little extra wave in there, which is actually a phi relationship. We have the R wave and the T wave that are in phi relationship to each other, but that's another story. That's just an interesting fact. Okay, so man's cycle is 1 second. Because our heartbeat is approximately 1 second, it's a convenient time interval for calibrating devices. Okay, for calibrating the universe. So this is our calibration parameter, just like 1 meter is the calibration of space. So this is our calibration parameter. This is man's cycle. Nature's cycle is the period. Okay, nature doesn't know what a second is. Nature's cycle is the period. So this equation, lambda equals c over f, this equation is a transformation from man's period, or woman, that's my inside joke, to nature's period, which is the wavelength. Nature doesn't know what a second is. Okay, nature only knows what a period is. And so this is nature's cycle. So all energy equations appear to be appear to be in the domain of per second. Okay, this is the domain of per second. All energy equations are per second. They have to be. We need per second, humans need per second to do experiments. We need a constant time interval in order to do experiments and repeat experiments. And so the second is our chosen time interval, just like the meter, just like the kilogram. These are arbitrary calibration parameters that we use to do our experiments and to get results and to correlate the numbers. So there's nothing wrong with this. There's nothing wrong with doing it this way. I'm not advocating that we switch to per cycle. We need per second. This is how it's done. The problem is with the language, with what we say, with how we interpret this equation. The output of this equation cannot be fundamental because it's a variable. It can't be fundamental. This is fundamental. And what I showed in my last video is every wavelength of light contains, carries, is responsible for the same energy H. This is the photon. Okay, but here's the problem. Let's do this. Okay, so I was having a discussion with someone and they were bothered by my diagram. So here was my diagram. I've got a picture of the Earth here and the moon over here. And the Earth and the moon are approximately 350 million meters, okay, apart. And we know that light travels 300 million meters per second. Okay, so that's approximately, let's say it's here. So this is 1 second. 1 second. Okay, so if I shone a light from the Earth in 1 second, it would get to here. It would be there. Whatever the light looks like, whether it looks like this or whether it looks like this, that's usually how photons are drawn. Okay, and this was the argument I was having with a colleague of mine. Okay, so they saw, here's, do it again, Earth and the moon, and there's our point in between. Okay, I drew this, okay, and they saw this, because that's how a photon looks in their mind. And so what I was drawing was 1 wavelength, okay, but what they saw was this. They saw 2 wavelengths. Okay, so it's just it's a confusion in the way things were drawn. I was drawing a schematic of a wave, but because they wanted to see the photon, they were turning it into 2. So basically what I'm doing is that 1 wavelength, this is 1 wavelength of a photon. They like the photon, they're hooked on the photon, so I'm going to draw it like the photon. Okay, so let's do this again. Here's the Earth, and here's the thought experiment that I was doing at the time. Okay, so let's assume, so here's our equation, E equals HF. This is, and there's a little t in there, or I could draw it over here, it doesn't matter. Okay, equals there's a t in this experiment, and it was set equal to 1 second historically, and that's where all the problems started, I believe. And the problems are only with interpretation, they're not with the physics. The physics is fine. Okay, so let's assume that I have a little light source. So there's my 1 second mark here, and this is just to help visualize. There's nothing important about the Earth and the moon in this picture other than to visualize how quickly light gets from here to here in 1 second. Okay, it gets almost all the way to the moon. So I'm going to draw a 2 hertz photon the way my colleague wanted to see it. So there's 2 photons, okay? And there's the peak of this photon and the peak of this photon. So according to modified unit analysis, each of these contains H. Okay, this is a 2 hertz. This is a 2 hertz signal. However it looks, okay, I would draw it like this, right, where I've got 2 wavelengths, okay. I draw it like this, but they wanted to see it like this, so that's fine. I'm going to just get rid of that so it doesn't confuse anyone. Let's see. Okay, so here is a 2 hertz signal. Now this could be 2 photons, or it could be 1 photon that after a certain amount of time it's here, and then after a certain amount of time it's here. Okay, or it could be two photons. If I have a light that's continuously shining, then I'm going to have a photon here and a photon here. Each photon, and I'm calling it a photon because a photon is supposed to be a fundamental particle, and to me fundamental particles have to have the same mass or energy. Okay, all electrons have the same mass energy, and all protons have the same mass energy, and so they are fundamental. So here is what I believe is the photon, okay, and it has energy h. And here I've got two photons in approximately 1 second, okay? So I plug 2 into this equation. I plug 2 into this equation, 2 times h, and I get the energy of a photon. But it's not the energy of a photon, because this is a photon. This is the energy of 2 photons, because in my 1 second time interval only contains 2 photons. Or it could contain 1 photon that oscillated twice. Either way, this could not be the energy of a photon, because there's 2 in here. And that's my point. That's my thought experiment, and this is what has bothered me for quite a long time. Because if a photon travels in one, let's say this is the same photon, so here's 1 photon, and after a certain time interval it's over here, okay, it's 1 photon oscillating twice in this time interval, and so I put 2 into here, and I still don't get the energy of 1 photon. Okay, I get the energy of a photon after it has traveled for 1 second time interval. So this is where the problem lies, I believe, because E equals HF cannot be fundamental. It can't be fundamental because E is variable. Okay, I'm going to do this again. Okay. Let's pick yellow. There's the Earth. There's the Moon. And now, there's the 1 second mark. Okay, 1 second. And now I'm going to do a higher frequency photon, only I'm going to draw them as circles because circles are easier to draw. They're very much like circles. So I'm going to draw a bunch of circles from here to approximately here. Okay, so in 1 second, now I've got 1, 2, 3, 4, 5, 6, 7 cycles. I have 7 cycles, so E equals HF. I plug 7 into here, multiply by H, and I get an energy of whatever this is. Okay, so this can't be a photon. It can't be a photon. It's not fundamental. If I plug in a different frequency, I'm going to get more or less of these circles in this space. Or I'm going to get, or it could be 1 photon. So at one period it's here, at the next period it's here, at the next period it's here, at the next period it's here, and here and here. Okay, so this is the energy of 1 photon as the number of times it's oscillated in a 1 second time interval. Okay, so this cannot be the photon. This is the photon. This is fundamental. This is H, this is H, this is H. Regardless of whether there's a bunch of photons or whether this is 1 photon that's at one point in time it's here, and at the next point in time it's here, then here, then here, then here, then here, then here. It doesn't matter. Either way, 1 second is in the domain of per second. Okay, so whenever there's a frequency term, you're in the domain of per second. So this is the energy of 1 second worth of H oscillations. 1 second worth of photons where the photon has energy h. And that's basically it. That's where I'm going with this. So let's do this one more time. Here's the Earth. Here's the Moon. Here's the 1 second point. Okay, so this time we're just going to ignore whether it's a wave or whether it's a photon. I like to draw a wave like that, where this is the wavelength, this is 2 pi. Some people, when I do that though, they see this, where this is the wavelength, where this is the photon. So just for the sake of simplicity, okay, I'm not going to do any of that. Let me get rid of this. Okay, so let's pretend that we have a light source on the Earth, and it is capable of emitting, let's say, 1 photon at a time. And let's say that that photon is in the millimeter wavelength. Okay, so that would be 0.001 meters. Okay, so that's the microwave, in the domain of the microwave. So, but let's say we can send 1 photon, whatever that is. It's a wave, it's a particle, it's an impulse, whatever you want to call it. Okay, so so we know after 1 second that it's going to reach the detector. Now let's pick a different color here. So here's a photon that reaches the detector in exactly 1 second. 1 second. So that's all we know, really. And we know that after 1 second, that photon has traveled 300 million meters. 300 million meters. And that's about all we know. So after 1 second, the emitted light was absorbed by the detector. After 1 second, it reached the detector, which is here, and got absorbed by the detector, and it traveled 300 million meters. Okay, so what else do we know? We actually don't know. We don't know exactly what's going on between here and here. We don't really know what's going on because we can only see a photon when we detect it. We can only see a photon when it reaches this point here. Okay, but what we do know is that light has frequency. So light must be an oscillating something. It is oscillating. We know because it has frequency. If it didn't have frequency, we wouldn't have a wavelength. And the wavelength we know is in the millimeter domain. So where does frequency fit into all of this? And this is where I want to get into these pictures on the left here. Okay, so we know these are simple harmonic oscillators. This one is the pendulum, this one is the spring, and this one here is an LC circuit, or they call it a tank circuit. And this circuit generates an oscillation. So this is an oscillating circuit. Okay, so I think light is closer to being like this than it is to the other two, but they all basically do the same thing. Okay, the pendulum swings between potential energy and kinetic energy. So when the pendulum is, let's just get a pen here, draw a pendulum. Okay, so here's the pendulum. When the pendulum is up here, it's got the maximum potential energy. And when the pendulum is down here, it's got the maximum kinetic energy. Then when it goes back up here, it's got the maximum potential energy again. So light is continuously sloshing between potential and kinetic energy. Okay, so that's what the pendulum does, and that's what all harmonic oscillators do. The spring over here bounces up and down, and it as well is continuously sloshing between potential and kinetic energy. When it's at the bottom of the swing, it's got maximum potential energy. Halfway through, it's got maximum kinetic energy, and back up at the top, it's got maximum potential energy. So these two things, the pendulum and the spring, are continuously moving back and forth between potential and kinetic energy. The LC circuit is doing the same thing. Okay, the capacitor, okay, let me get a pen here. The capacitor stores potential energy, and the inductor, it doesn't want me to draw a coil, but that's okay. The inductor stores kinetic energy. Let me draw that a little nicer. Okay, for some reason, strange, but anyway, so the capacitor stores potential energy, and the inductor, I guess I have to go slower, stores kinetic energy. And here is the tank circuit. So what does this tell us? If light, since light is an oscillating circuit, it must also be sloshing back and forth between potential and kinetic energy. Let me pick a different color here. So we know that it is, let's say the potential energy is, let me pick a pen, the potential energy, so that I'll do the potential energy making it small and the kinetic energy making it big. So it's continuously sloshing between potential and kinetic energy. And the kinetic energy would be the transverse part of the wave or the signal. Let's just call it a signal. So here is what we have, dot, 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 and then all the way over to here, okay, until it reaches the detector. So we know the light is oscillating, and we know that in the millimeter wavelength, the frequency of a microwave in this particular 0.001 of a meter or 1 millimeter has the frequency of 300 billion cycles per second, right? We know that it's oscillating 300 billion between the Earth and this 1 second mark, right? Between the Earth and this 1 second mark, this frequency, the frequency is also this wavelength, this type of light is oscillating 300 billion times per second. So there's 300 billion oscillations between here and here. So what does that tell us? So what do we know? We know that when we emit the light, it gets to here after 1 second. And we know that the wavelength, when we get our little tick on the other side, this is a detector over here, and it detects, let's say it detects only microwaves. So I send one photon, I send one oscillation, one signal, one pulse from my emitter. I send one pulse, and it travels to here and oscillates in between 300 billion times before it gets to here. So this is our frequency. This is our frequency that we call hertz. Okay, so using our equation, E equals H times frequency, and we know there's a little 1 in here for the time, okay, because there's actually a time variable in here that was not written because it was set to 1 and subsequently buried, okay. So we know the light is oscillating 300 billion times. So we plug 300 billion into the frequency term, we multiply that by h, and we get an energy term. It seems obvious to me that this energy term is in the domain of, let me pick a different color, well, that's not working very well, per second. So in 1 second, this photon, whatever it is, oscillates 300 billion times before it hits the detector, and the detector registers 1 photon. Now surely this photon doesn't accumulate, so each of these is h. Each of these is h, it has to be, because we're multiplying the frequency by h. So each of these has to be h. And the problem that I'm having, or problem that I was having, is what is h? Well, h must be the energy of each of these. You multiply the number of these between the Earth and the 1 second mark by 300 billion hertz, and you get an energy term. But that energy term is associated to the number of times that this wavelength, that this photon oscillated in a 1 second time interval. So again, this cannot be fundamental. Seems pretty clear to me, but for some reason I still get some objections to this. But that is not what I'm getting at today. But the point of this video has more to do with this equation. Lambda equals c over f. And what I'm saying is that this equation is the transformation between the domain of frequency, the domain of per second, and the domain of per cycle. Okay, so the domain of per second is not the same as the domain of per cycle. The domain of per cycle, the wavelength is 1 cycle. Okay, and the domain of per second pertains to many cycles. So they are not talking about the same thing. Okay, what I'm saying is that every wavelength of light has the same energy, h. And then you add them all up over a 1 second time interval, and you get the energy of that 1 second time interval as if either a bunch of photons were sent in the 1 second time interval, or 1 photon was sent, and that's the number of times it oscillated. So this equation, E equals HF, is a little bit ambiguous, because does it mean it's 1 photon oscillating 300 billion times for the microwave? Or is it that if you send a continuous signal and let it oscillate 300 billion times, you're going to get 300 billion photons in 1 second, and you're going to plug that into this equation and you're going to get the same answer. So the interpretation of this equation is a little bit ambiguous, and that's what I'm trying to do. I'm trying to disambiguate this equation, because this equation is in the domain of per second, and it's not a problem. It's not a problem. It's just the problem I'm having is when people say, when a physicist says that every wavelength of light carries a different energy, because that doesn't seem to be true. When you break it apart and you look at it this way, it doesn't seem to be that every wavelength carries a different energy. It seems that every wavelength carries the same energy, which makes this fundamental. So H is fundamental. E is not fundamental. So here's where it gets interesting. Okay, I'm going to erase this. And here's where quantum mechanics kind of gets a little confusing. because sometimes they write equations in the domain of per second, like this one, E equals HF. Okay, that's in the domain of per second, or they write it in terms of frequency, I should say. So sometimes they write their equations in terms of frequency, and sometimes they write their equations in terms of wavelength, like the de Broglie expression, which is momentum equals h over lambda. Now, at first glance, you might think that this equation is written in per second and this equation was written in per cycle, but that's not exactly true, because this h is still the standard h. Okay, in modified unit analysis, I add a t. And then I call this HQ. Okay, so I called it, now this has the units of J per cycle. Okay, H has units J per cycle. Okay, so for this equation, the per second is still embedded into the equation, so this equation is still in the domain of per second. Okay, so I'm going to rewrite this. So momentum equals HQ times T. So this is how I would do it, over lambda. Okay, then I divide both sides by T. Okay, these two cancel. So I get, now momentum divided by time is force. So now I have a force equation, which is really neat. And then I've got HQ. Okay, and then I'm going to convert this to the frequency domain using F equals C over lambda. Okay, using the original equation that we've been talking about. So I'm going to write HQ over C times the frequency. So now I have an equation in the domain of frequency that looks a lot like the original energy equation or power equation as I do it in modified unit analysis. As well, HQ, which is Planck's constant over the speed of light, forms another constant of nature. So I'm going to talk about that in another video, but I just wanted to show you where I'm progressing with this line of thinking. So now I have two equations that look really similar. I have power equals energy over time, just to be clear, equals HQ times frequency. And now I have force equals momentum. Now this is momentum. I know they use P everywhere, but that's momentum over T. So momentum over time is force. Okay, force equals HQ over C, which is another constant of nature, times frequency. So now I have two equations. One is in terms of power and one is in terms of force. Each of them has a constant term. Okay, here and here. Okay, so HQ over C I call the quantum of momentum, or PQ. Okay, and this is useful. This can be used, and in future videos I'll show you how I use it